Okay, this is the notes for section 5.3, solving systems using substitution. If you haven't done so already, make sure that you pause the video at this time and go back and read 5.3 before moving on with these notes. So in your Algebra 1 course, you were looking at systems, and one of the methods that you used of solving systems was substitution. So in this section, really, we're reviewing that method. We'll go a little deeper. We'll do a little bit more with word problems in it. But the ideas are the same as what you had in your Algebra 1 course. The thing that you want to remember about solving systems using substitution is when it works best. And if you want to think about this for all of the different methods. But solving systems using substitution works best when you have your system, at least one of the equations is solved for one of the variables. Okay, so let's take a look at example 1 here. It says solve the following system using substitution. And we have y equals x minus 7 and 2x plus y equals 5. This is a perfect example of a situation where we might want to use substitution. You'll notice that we have y is equal to x minus 7. So we can take that x minus 7 and substitute it into y down here in this equation. Okay? So what I'm going to do is I'm going to rewrite the bottom equation, taking y out and putting x minus 7 in. If I do that, we can then solve for x. So you'll notice that I've rewritten the bottom one, I took y out, I put x minus 7 in, and then I went through and solved. Once I've figured out what x is, okay, now my goal is to find the one point that is the solution to those two lines. So what I'm going to do is, or the intersection of those two lines, if you think about it graphically, is I'm going to take my x value and plug it in to y equals x minus 7 to find my y value. So I do that to get y equals negative 3. Therefore, the point that they share, the solution set to that system, is the point 4, negative 3. Okay, another way that we can use substitution to solve systems is when we have systems that involve, say, more than just two equations. So I have an example here of this type of situation, and once again, it's one of those things where you want to try and get one of the equations all in terms of one of the variables to help you kind of solve for the rest of the variables. So here's what it says. It says Trevelyan Stadium has a seating capacity of 4,216. There are 4 times as many lower level seats as there are upper level seats, and there are 3 times as many mezzanine seats as there are upper level seats. How many seats of each type are there? Okay. Well, just to kind of the setup here, I'm gonna lay out what I want to do. There's 3 things I want to find. I want to find the lower level seats, the upper level seats, and the mezzanine seats. So I'm going to let these variables equal each one of those. L for lower, U for upper, and M for mezzanine. Well, if that's the case, I know one of the equations that I can write, since there's only those 3 types of seats in the stadium, is L plus U plus M has to be equal to the total number of seats. Okay? Then they gave us 2 other relationships in the statement. They said there are 4 times as many lower level seats as there are upper level seats. Okay? So if I take 4 times the number of upper level seats for U, that would be equal to L, the number of lower level seats. So there's a second equation that I can use. And then finally it says there are 3 times as many mezzanine seats as upper level seats. Well, that means if I take 3 times U, that would have to be equal to the total of mezzanine seats. So now I have 3 equations and 3 unknowns. I should be able to solve this for each of those variables. Now, you'll notice that both L and M can be expressed in terms of U. So what I'm going to do is I'm going to replace L with 4U, and I'm going to replace M with 3U. Therefore, this top equation, when I rewrite it, will be all in terms of U. So if I do that, okay, here's where I'm at. Now I can then combine my like terms and get 8u equals 4,216. And then I can say, well, then u is equal to 527. Then to find L, we just use the equation for u is equal to L. I can plug 527 in for u, which would give me 2,108. And to find the mezzanine seats, I'm just going to use 3u is equal to m. Therefore, 3 times 527, which is 1581. And we've now solved for all three of the different levels of seats. Okay, another situation that we can use substitution to solve systems is in nonlinear systems. So it doesn't always have to be two lines when we're using substitution. This is a perfect example of the type of problem where we could use substitution. We have the system y equals 3x and xy equals 48. So one of the equations is solve for y. So y equals 3x. So what I'm going to do is I'm going to take that 3x and I'm going to substitute it in for the y down here in this equation. Okay? So if I do that, I get x times 3x is equal to 48. Well, that would be 3x squared equals 48. If I solve this for x, remember if you have x squared equals 16, that means that there are two solutions, both 4 and negative 4. So to find the y values, what that tells me is that there's going to be two ordered pairs that are solutions to that system. So if I think about it graphically, there's going to be 2 points of intersection between that line and that curve. So if I do that, if I plug my x values in for y, I have to plug both of them in. So 3 times 4 is 12. That would be one of my y values. And the other one is 3 times negative 4, which is negative 12. Now, all of those four numbers are not interchangeable. 4 and 12 are paired together, though, so that's my ordered pair. And negative 4 and negative 12 are paired together, so that would be my second ordered pair. So this right here would be my solution set for this system. Alright, the last idea I'd like to take a look at here is the idea of consistent and inconsistent systems. Basically almost all of the systems that we've looked at so far have been consistent systems, because all a consistent system is a system that has one or more solutions. So if you think about all the examples we've just done here, 1 through 3, all of them have at least one solution, therefore they would be considered consistent. Example 4 in your book, okay, in which you might want to reread that one, but that also is considered a consistent system. The idea of an inconsistent system then would be any system that has no solutions. Okay? Okay, let's look at example 4 here then. It says solve the system x equals 3 minus 2y and 3x plus 6y equals 6. So once again, it works out really nicely for substitution because I can substitute what x is equal to in for x in this bottom equation. So that's what I'm doing over here. And as I do that, and I go through and I do my solving, I end up with 9 minus 6y plus 6y equals 6. Well, it turns out that my y terms cancel out and I'm left with the statement 9 equals 6. Well, that's a false statement, okay? And any time in the process of solving a system, if you end up with a false statement like that, that means there's no solutions and it is an inconsistent system.